Hi, welcome back. This video is on the force on magnetic materials in order to do or to perform useful work. So what I mean by that is that first we can make useful devices like electromagnets. So this is the example that I have in front of me here. But we can also build relays, which is like a switch. We can build rotating machines, and we can also analyze or build magnetic levitation systems. So let's take a look at this electromagnet. In this electromagnet, I have some ferromagnetic material, steel, and then I have a current carrying wire that's looped around the steel n times. And the idea is that this is going to make a magnet that will attract this ferromagnetic bar down here, and it's going to move the bar a differential length dl. So we've been talking about how we can analyze this thing with circuit analysis techniques, which you know that I love by now. And this is a big series circuit where the air would have reluctance, right? And the steel itself would have some reluctance as well. So it's a big series circuit. That is to say the flux through the system is the same. And if the cross-sectional area does not change anywhere in this magnetic system, that is S does not change, then that means the magnetic flux density does not change. It's the magnetic flux divided by the cross-sectional area, at least the magnitude of the flux, magnitude of the flux density. Now, we can ask ourselves what force this would be attracted with by considering the work required to move the piece. The work and the energy are the same. So the energy or the work required to move the piece would be F dot dl, or F times L, since F and L are in the same direction, and the negative is, this is the work energy theorem, the negative says that we are closing the gap, so we need that negative there. So we want to know, well, how is this differential work, that is the work required to move this thing dl, how is this related to the magnetic flux density B? And if you remember, we said in a previous video that the energy density was 1/2 mu h squared. Okay, that was the energy density, so that was the energy per volume. And of course, remember that that in free space or in air, we have that B is mu0 h. So actually, I can put this in, and I can say that this is 1/2 mu0 times mu0, B over mu0 squared, and then we would see that this is 1/2 B squared over mu0. Okay, so I've related it to B now, and so this is the energy density. This is the energy per volume. So now if I wanted the energy, I would have the energy per volume, and I'm using mu0 because we're talking about the air gaps, now times the volume, so the volume of air there. And so what is that? Well, that's the cross-sectional area, S, ignoring fringing effects, and then times the length, right? That's the volume of the air that's in that gap. And so now we have the energy that's there, the magnetic energy that's there, and that's in one gap, right? And because there are two reluctances that we have to worry about, and so we would add, in other words, we have two forces that are working together to do this. So we would have this as our total energy. And also from a previous video on energy, let me remind you that we had delta W was 1/2 mu h squared, delta x, delta y, delta z, right? This is actually the same thing. This is delta V, the volume, right? So what we're saying is that we're considering this now the area S, and this is the length dl, you see. And again, we've made this substitution that B is mu0 times h. Okay, so now we can just we can solve that. The dl's drop out, right? We can solve that for F, and we get the force on this thing is negative b squared s over mu 0. So the absolute value of that is of course the magnitude of the force. Excellent. So that's the force that this thing experiences. Of course, half of the force is over here and half of the force is over here. Just like we added half the force here and half the force there. Also, we can talk about pressure. The pressure, then, is, of course, in newtons per square meter, right? The force per area. So lowercase p, the pressure, not to be confused with rho, is the force per area. So that cancels with that s there, and we get, in terms of absolute value or in terms of magnitude, the pressure at each one of these gaps would be b squared over 2 mu 0, because remember this was the total force, and so the force at each one is actually half of that. And so now if we talk about the pressure at each one, that's where the 2 comes from, and the s's drop out. And if you recall, hopefully you do, this was, well, we can write this actually before recalling. We can write this as 1/2 b times h, again with this relationship here, right? And then if you recall, this was precisely what we called the magnetic energy density. And so we see now that the pressure, if you want to relate this to mechanical systems, is equal to the magnetic energy density. Nice. All right, so I think that takes us to the end of static fields, static electric fields, static magnetic fields. I think we're ready to start talking about time varying fields, the electromagnetic field. I will see you then. Thanks.